Hi everyone, me again. So the previous talk, we talked about the stochastic soaring raptor simulator, or SSRS in short. That model is based on some preconceived notion of how a golden eagle would travel by minimizing the energy, but it was not data informed. It was validated with data, but it was never calibrated. So now I'm going to talk about a model that we're building that addresses some of the shortcomings of the SSRS model by using the telemetry data. So let's talk about the data that we have. So we have two sets of data. One is in Western US in Wyoming, right centered at top of the world wind power plant. And we have data from Eastern US, as you can see on the right here. So the red dots you see are turbines. So you can see on the Western US side, we have 2,500 turbines within this region where we have the data. And on the right, in the Eastern US, we can see there's 1,800 turbines. So there's a lot of overlap between golden eagle movements and turbines. So we need to use this data to understand how the golden eagles behave, how they move, and if we can use that information in a parametric fashion to create a predictive model. Now, I should note that the data on the right is from 2009 to 2020. So the older data set was captured by the units that were not sampling at high rates. So probably at 15 minutes interval. So that's why you see less data points, even though the time interval is more. The data on the Western side is newer GPS units that they capture data at very high temporal resolution, like 3 seconds, 6 seconds. So this is useful for us to then build a model that can simulate golden eagle movements at that scale. So a little bit about the data collection. So this is, I'm showing on the right, what we have, what I showed in the previous is a subset. So the data on the left here is a subset of the data that I'm showing here, because we wanted to focus on a smaller region, and so that the terrain aspects and the climate and everything remains same in that region. But you can see there are like 5 northern migrants, 3 southern migrants, 36 residents. So the data that we have is mostly residents, but you can see the migrants going all the way to Alaska here. And the data was collected from 2017 to 2020. But the data we're going to use in this model building is a subset of this data that I showed in the previous slide. So what do we have in this data? We have time varying variables, so horizontal location X and Y in projected coordinate system. We use North America Albers equal area conic projection. We also have lat long, but we deal with the X and Y coordinates in meters. We have altitude above sea level. We have horizontal speed that's captured by the unit. It's not the finite difference one, it's the actual measurement from the unit. The heading information, which way the bird is oriented, or the unit is oriented. The error radius, so we have horizontal dilution of precision and vertical dilution of precision, and then we can get the error radiuses from that. And they are time varying as well. And the number of satellites and the temperature of the unit. We have age of the bird and the sex of the bird. That's obviously not varying with time. And we use these information to capture some derived variables. So we are using USGS 3DP data set to get the elevation, slope, and aspect under each point in the telemetry unit. So there's 3.6 million points. For each of that point, we can get the elevation, slope, and aspect underneath where the bird is. We can get the closest turbine location. So USGS US wind turbine database is updated monthly. So we can go back in time and look at that point and then figure out what was the closest turbine at that point. And its hub height and blade length. We can also get wind conditions using NOAA's HER data set that we just talked about. This is a capability that we're currently developing. It's not there in the SSRS, and we have not yet annotated the data, but it's coming. So once we have wind conditions and other variables, we can then annotate each point in the telemetry data with the wind conditions at that point. So that's work in progress. If you want more details about the data collection, please contact Trish Miller from Conservation Science Global. She's the one who knows in detail about the data collection and data filtering processes and all that. So please contact her for more details. Okay, so let's look at the data. So first thing we have to do is we have to get rid of false fixes. So what I'm showing here on the top is a track around noontime, 15th May 2019. You see that big jump in the altitude above ground level. That's a false fix. That means the unit was capturing something, and then it realized it was not properly fixing the location, and then it moved to the actual location. So we need to remove this because this will introduce biases in our modeling process. So, but at the same time, we don't want to remove valid movements. On the bottom, you see at 2:23, 20th April 2020, the bird dived from 500 meters at 90 miles per hour. So we don't want to remove that, but we want to remove the false fixes. So we have to be careful when we filter the data that we keep these movements, these outliers in the data set. Yeah. So this is the approach that we took. So we had 5 filtering steps. So first we remove all the data where the altitude above ground level of the bird is below -50 for 1 minute or longer. So if it was just for 10 seconds, we keep it because that might be, there's errors in the telemetry unit data collection. So it might be because of errors. So we don't want to just remove that. But if it happens for 1 minute or longer, we remove it. We remove all the horizontal speed data points that are below 0.1 meters per second for 1 minute or longer. The bird may be perching at that time, so we remove it. We remove all the data that's less than -100 meters. AGL, we think that might be because of false fixes. But we're keeping from -100 to 0 because there are errors in the vertical location that's captured by the unit. And then there are errors in the digital elevation model from USGS 3DP that might introduce errors as well, right? So we want to keep those. And we remove all the horizontal speeds higher than 50 meters per second. Those are, there's very few data points that has that. And we also remove large changes in vertical speed. And that will, the last one actually takes care of that false fix track that you see in the top. Once we filter that data, we want to create tracks. So we want to say, okay, anytime there is a time difference of more than 30 seconds between 2 data points, put them in a different track. And we only keep the tracks that are at least 4 minutes long and have at least 40 data points. So then we segment the entire telemetry data into tracks that are independent from each other. And each track is at least 4 minutes long. And the time interval, the sampling interval is equal to or less than 30 seconds for the entire track. This gets at 60. So for the Wyoming data set, this filtering and everything is for the Wyoming data set, but a similar process will follow for the Appalachian data set. We end up with 65% of the data. We got 9,400 tracks, and the median track length was 40 minutes. So we think this is a right optimal process, and we are not just discarding data too much, and we have 9,400 tracks. The next step, once we have these tracks, individual tracks, we want to take care of the sampling rate. So what I'm showing on the right here is the DT, the time difference between one point and the next point in the Wyoming data set on the top and the Appalachian data set. So you can see the DT is not constant. For the Wyoming data set, you can see about most of the data is at 6-second interval and 3-second interval, but there's all the time intervals are out there. So it's not a constant DT. You can see for Appalachian, the higher DTs are more pronounced because of the older units, some of the older units used in collecting that data. So, but 82% of the Wyoming data set is under 30-second DT time interval. And 52% of the data in the Appalachian data set is under 30 seconds. Yeah, so we want to handle that first. And then once we have the data at constant time interval, we can then look at the statistical parameters of this data. So how do we deal with that? We start with a stochastic motion model for each track. So we have a constant acceleration model. So the position is dv by dt, velocity is dA by dt. dv by dt is acceleration, dp by dt is velocity, and then acceleration is assumed as a random process, a Gaussian white noise process with some variance. We take that model and we put it in a stochastic state space model structure. So our X is our state space for each bird. It captures the location, the velocity, and acceleration in each direction. So we deal with X direction, Y direction, and the Z direction. So 3D, three directions. So for each direction, we do this. And we build this stochastic state space model. And then we have the measurement equation, and that's where the telemetry data comes in. So for example, for vertical measurements, we have the altitude captured by the telemetry unit goes in dk. That gets related to the state space. And then we add this noise, that's measurement noise, that takes care of the error information from the telemetry data and also the error in the digital elevation model. Because the altitude above ground level that's computed has errors introduced by the altitude that's measured by the unit, the errors from the digital elevation model, and the errors in the horizontal location, because we use that location to figure out where the bird is and then get the ground elevation underneath that point. So there's three errors that are there. So we can take care of those errors. So this approach basically handles uncertainties in the data. If we just do linear interpolation or spline interpolation, we're assuming the data is perfect. So that there might be some things happening there that we're ignoring. So this stochastic approach lets us handle uncertainties in a principled way. Yeah. And we use that model structure and put it through a Kalman smoother. So a little bit about Kalman smoother. So it's a combination of forward Kalman filter and backward Kalman filter. And Kalman filter basically allows you to merge a stochastic model with noisy data in a robust way. So a robust noisy time series data. So I'm showing here one sample track from those 9,400 tracks when put through this Kalman smoother. So on the top, I'm showing the altitude above ground level. So the red dots you see are the actual measurements. And the green region is the 95% confidence bound that we get from Kalman smoother. So we're not only getting the actual mean, we're also getting the uncertainties in the altitude above ground level, the vertical speed and vertical acceleration. And that's useful because then we have propagated the uncertainties in the altitude that's measured by the telemetry units all the way to the actual state parameters, which are speeds, accelerations, and location. And on the left, you see the horizontal motion. So one thing that we wanted to test was what DT is appropriate. And this is at 1 second. And the reason we chose 1 second was it was enough to capture these soaring, convoluted soaring behaviors. You see the small circles. If you choose like 3 seconds or 5 seconds, we miss those. So the 1 second interval of Kalman smoother lets us make sure that we are not missing these, because these are important maneuvers that golden eagles are doing, and we need to capture that in the model. Yeah, so we have uncertainties information and acceleration, speed, and altitude, and same process goes for X location and Y location. So we have all the parameters in the 3D movements. Once we have resampled the data, we need to then use this data to build a movement model. So first we look at the distribution. So what I'm showing you are 9 motion parameters. So I'll go one by one. First is altitude above ground level. And we know that all these 9 for each track. For 9,400 tracks, we have these 9 parameters, time varying at 1 second interval, and their uncertainties. So we have altitude above ground level, we have horizontal speed, we have vertical speed, we have tangential acceleration, we have radial acceleration, vertical acceleration, angular speed, radius of curvature, and curvature. Curvature is just 1 over radius of curvature. And so we wanted to test whether our resampling whether we're not doing something wrong. So I'm showing on the top 3 marginal distribution. I'm also showing the distribution that we computed using the actual telemetry data, nothing done with it. And you can see the match. So that makes us think that we're not doing something terribly wrong. The distributions from the Kalman smoother resampling process matches with those from the telemetry unit. So we have these 9 motion variables that we're going to use to build a movement model. And we take a route of conditional distribution. So we want to know how the mean of one parameter varies with the mean and variance of the other parameters. So for example, I'm just looking at 3 motion parameters here: vertical acceleration, vertical speed, and altitude above ground level. We're saying the mean of vertical acceleration is a nonlinear function of vertical speed and altitude above ground level. And that we can see it from these conditional distributions. So these distributions are basically, I'm plotting vertical acceleration when the vertical speed falls within these bounds that you see. So there's a nonlinear relationship going on with vertical speed and vertical acceleration. So we need to capture that. And same, we can do it with variance. Since we have variance information from Kalman smoother. Kalman smoother, by the way, assumes Gaussian behavior for all the motion parameters, which is reasonable in this case. But we can basically build these models easily because we're not fitting it to the actual tracks. We're fitting it to the distributions, which is very low dimensional than fitting it to 9400 tracks. And then once we have such a function, we can then tune the parameters using these conditional distributions. So taking this example, for instance, we build a model of vertical acceleration, how it varies with vertical speed and altitude above ground level. And we estimated its parameter. It's an algebraic equation. I'm not going to go into details, but it's an algebraic equation, and we use a way to test whether the model has fitted right or not using some cost function. And these are 3 tracks that we have simulated using that model. And so these tracks only use information between where. So once it simulates vertical acceleration, we can then simulate speed and then altitude above ground level using the stochastic model that I showed earlier. So all we need to simulate is acceleration, then comes the speed, and then comes the location. And these are 3 sample tracks that we have simulated using just the relationship between vertical acceleration and vertical speed and altitude above ground level. And they look sort of reasonable, but we are looking into improving those by including the horizontal speed and other motion variables in that. One thing I would note here is we're just dealing with these 9 motion variables. And we are hoping, or we are assuming, that the other parameters such as reliance on updrafts or the equal activity are implicitly captured in those functions through this data calibration approach. But in the future, we will be looking into explicitly including them along with these 9 variables. You'll have ground slope, aspect, wind conditions, updrafts, closeness to a turbine. So we'll be including all those parameters, but we're just starting with these 9 for a moment. Yeah, so next steps are explicit consideration of atmospheric conditions, as I was saying, creating a 3D agent-based movement model that is calibrated using the telemetry data. So right now I was just showing the altitude above ground level, but we need to simulate the horizontal position as well to make it a 3D model. And then merge this with the SSRS model that was 2D to create a model that works in any scenario and is data informed. And 3D is important. I just want to mention that 3D movement model is very important because in the last talk, I was talking about presence only because for us to compute risk, we need 3D movements. That's why we kept saying relative presence map, because that model was only horizontal. But when we have a 3D model, we can then compute the risk from presence.